Um, right, so thank you for that very kind introduction, Ivan. So the purpose of this presentation is to give you an overview of KLM-style defeasible logics, which the previous two talks have also done a fair job at, and then to give us an idea of where we think this field can go in the future. So, right, so to give the background, like the previous talk, we start with the classical propositional logic, which is intended to reason about statements and the relationship between statements. So again, we see the birds example, but we can, I won't spend too much time on this part, but you can formalize the notion that birds fly by reasoning about the statements of it is a bird and it flies, and we can encode it is a bird as alpha, it flies as beta, and we can have a logical implication relationship between those statements. And what this does is it strips the natural language representation of this knowledge from the sentiments that we put on through natural language, and it just preserves the structure of the actual knowledge. And so we have to provide our own sense of meaning, which is done through the propositional semantics. And in propositional logic, this is done through imagining a set of possible worlds where each world is a unique interpretation of these statements. So the world where it is a bird is true and where it is false, and the world where it flies is true and false, and so on, for as a permutation of every single atomized statement that we have. Using these semantics, we can define the notion of classical entailment, which has been spoken about in the previous talks. But over here, I wanted to just visually represent what is happening with classical entailment. So if we have in the bottom visualizations, each black dot representing a possible world, and if we have that square represents some set of statements and circle is some statement, then the worlds that are encircled by the shapes represent the worlds that satisfy the structure of knowledge in those statements or set of statements. And so if it is the case that our set of statements, every single world satisfying that knowledge also satisfies the statement, then we can say that it is entailed. And that's the case on the left. And if it is not, if there is some possible world satisfying a set of statements that don't satisfy circle, then we say that simply it is not entailed. A consequence of the property that if you add a statement to a set of statements, it will only ever constrain the possible world satisfying it. It'll never increase the possible worlds. We get the property, this is a semantic way of getting the property of monotonicity, which was also spoken about by Guy, which is essentially that if you add a statement to a set of statements, a previous entailment will never be retracted. What I've tried to do here visually is if you imagine the squares are sets of statements, if we add a statement to our set of statements square to have a smaller square that is satisfied by some subset of the previous worlds, it will always still entail circle. There will never be a statement you can add that will cause circle to be retracted. And monotonicity then is at odds with defeasibility. If you have a monotonic logic, there is no easy or simple way to reason about the notion that, say, a bird typically flies or something is typically the case. There are monotonic possibilities of trying to encode this knowledge. For example, you can say birds that are not penguins fly. But this sort of kicks the can down the road because you will have to update this for every possible flightless bird. And for example, an ostrich, or layers of exceptionality. For example, if you have a penguin with a jetpack, then this flies. And so you will have to then update with these layers of typicality as well. So the KLM framework, defined by Krauss, Lehman, and Magidor, try to approach this problem of getting some level of defeasible logic or defeasible reasoning by defining the ranked semantics, where rather than previously as we considered all possible worlds, in this, using a ranked semantics, we rank these possible worlds, where lower the ranking, the more typical a situation or a scenario it represents. So on rank 0 will be the worlds where birds fly and penguins do not exist. And at each level is a more atypical scenario or situation. And those possible worlds that rank infinity are simply those that are impossible. And there are many different ways of performing these rankings. You could rank these possible worlds in very many different ways. And since in each of these ranked models, as previously mentioned, defines a distinct defeasible entailment relation. And so there are many, many different kinds of defeasible entailment relations, different to classical monotonic reasoning, which is unique. And so these different defeasible entailment relations can be analyzed or thought of on the paradigm spectrum of prototypical and presumptive reasoning. And the intuition here is that they simply represent different patterns of reasoning, which you can consider different kinds of common sense reasoning. An example of prototypical reasoning on the left is if you know that people typically pay tax and they typically have full-time jobs, and you know that students are people that typically do not pay tax, you can prototypically entail that students typically do not have full-time jobs. Whereas if you use a presumptive entailment relation like lexicographic closure, you can reason about a very similar structure of knowledge. So we have that birds typically fly and they typically have wings. If we know that penguins are birds that typically do not fly, you can presumptively entail that penguins typically have wings. And one thing to note about these examples is that structurally they are exactly identical. They are isomorphic in the sense of what the actual connectives and the structure of the knowledge in place. But the sentiments are different to give you the intuition that these are tools to reason about different scenarios and that these kinds of different entailments can be domain specific. So to go over some applications about where defeasibility can be applied, we have the example of legal informatics, which is reasoning, applying AI or computation to the legal domain. And an example would be in deontic logic, which is a type of modal logic for reasoning about duty. So you can formalize the ideas of it is obligatory to pay tax, or it is permitted to drive, given that you have a license. Defeasible deontic logic has been shown in quite some recent papers to have some very interesting resolutions or solutions to known paradoxes in the field. And so another example would be in the field of formal argumentation, which is an inherently non-monotonic logic, an example of which is on the right, that reasons about statements and attack relations between statements. So if you have you can formalize an argument as a number of statements with attack relations, and you can select some consistent subset of those statements as a successful argument. And this is inherently non-monotonic. The other domain that we have selected as an example of an application for defeasibility is in programming frameworks such as Datalog. Enriching Datalog with defeasibility is quite a recent also field of research that has shown some very great promise, as well as an answer set programming, which is a programming framework that is itself inherently non-monotonic, where you can define constraints and using some logic, and then you can select answer sets or as solutions to those constraints. And this is a very, very vibrant and active field of research as well. So on the theoretical side of some future work for the KLM framework, we have selected an example of syntax sensitivity, which is the property that if you have a syntactic defeasible entailment relation, that is, it's defined with reference to the syntax of your knowledge base. The example is that if you have that birds fly and birds have wings as separate statements versus the classically logically equivalent single statement of birds fly and have wings, then if you use a syntactic defeasible entailment like lexicographic closure, you will either entail that penguins have wings or you will not, depending on which of those two structures you have, which of those two different sets of statements you have in your knowledge base. Explanation or explainable AI has been a very popular and vibrant field of research recently, and coming up with justifications, which is a very established method of explainable AI with classical logics, but to do it for the general case of a general defeasible entailment relation is a wide open question in the field. And then there is the problem of exporting defeasibility to more expressive logic, such as description logics, in which there is many open questions for defeasibility, as well as modal logics, an example of which would be the defeasible deontic logic, the previous slide. So to give you an idea of the kinds of problems that you have with typicality and defeasibility in more expressive logics, we can consider the situation where you know that elephants typically or usually like their keepers, and elephants usually don't like keeper Fred. And you have an example of Clyde the elephant who usually likes keeper Fred, actually. Then you have the question of, well, what is typically the case in the situation? You can approach and you can say that, well, either you have in the most typical situation, so the most typical worlds, all elephants like all keepers. But then this clashes with the statement that all elephants do not like Fred. So in all the typical situations, all elephants like all keepers, but also all elephants do not like an example of a keeper, which is Fred. And then you have another layer of atypicality where you say that, well, Clyde is an elephant that does like keeper Fred. And so you have these various clashes on these different levels of typicality. If you take this approach of, well, it's actually saying that in the most typical situations, this is the case. On the other hand, if you say that, well, what it actually means is that all the typical individual elephants, like all of the most typical individual keepers, then you have the case that, so all elephants do not like Fred, who is an otherwise typical keeper. And you can say, well, then maybe Fred is an atypical keeper, and that is why. But then you have an example of Clyde, who is a typical elephant who does not like Fred, the atypical keeper, which causes a clash with this intuition. And then if you say, well, they're both atypical, well, then what justification do you have for applying the first statement saying that all typical elephants like all typical keepers to them? And so these are the kinds of problems that you can, that remain to be solved, or that need some solutions, and importing defeasibility to some of these more expressive logics where you reason about individuals as well. And that is all that I have to say today. In conclusion, defeasible reasoning and logics has many interesting applications and avenues for research, more than are mentioned in this presentation, but including the ones mentioned here. Yeah, so I'm not sure how I'm doing on time, but I think we can move on to some questions if there are.
Yeah, so thank you very much. If you have any questions, please let us know. So in the meantime, I might have a question, maybe more than one. So, okay. So you mentioned possible extensions to languages that are more expressive than the propositional one, because of course they meet a variety of applications in AI, such as modal logic, of which deontic logic is an example, and description logics, which are the foundations of formal ontologies. So in your view, can you tell us what the main challenges in extending the KLM approach to these logics would be, and where we are more or less at the moment in doing that, from your current research?
So in the case of defeasible modal logics, I think that there's some very recent and good papers showing that, for example, I think he might be in the chat, but Julian released a paper showing that you can solve a very well-known paradox, as Forrest's paradox, about the duty to kill and whether you kill gently and so on, using defeasible notions. So if you enrich a deontic logic with a defeasible connective, saying that this is typically the case, then you can quite reasonably come up with consistent entailments and consistent inferences to these kinds of problems. In defeasible description logics, I'm sure you know as much where we are, but I think the main challenge, to my knowledge, is in reasoning, in A-box reasoning, which is essentially reasoning about individuals, and you get some very, very strange clashes, and it breaks to intuition when you try to apply defeasible concepts to the A-box naively. But in terms of T-box reasoning, it seems to be very, very successful. And I think there's some quite upcoming research, if not or recent research, that presents some possible solutions to A-box reasoning. But it's an open question, definitely. Does that answer the question?
You. Definitely.
Okay.
Do we have any other question? Please don't be so shy. So while we eagerly wait for your questions, I have another one, which for which I'm going actually to appeal to your psychic qualities, so to say. So in relation to the previous talk, right? If you consider that extension of the KLM approach with the Boolean operators at somehow the meta level, in your view, how much of the nice properties that you have in the non-nested fragment, in the positive fragment, would actually transfer to the resulting frame? How many of those interesting properties would you still be able to retain? And which ones do you think you would immediately lose? I have no clue on that. So then I just assume that you would have perhaps some hints on.
I
what the
think you
situation
might
would be.
assume, you might be assuming incorrectly. I would need
Okay.
some psychic abilities. My intuition tells me that you would probably retain quite a lot of the regular properties, the KLM postulates, simply because, well, the
Sorry,
Boolean,
just to make
yeah,
to make something more precise. By properties, I mean it very vaguely, right? I don't mean
right,
necessarily only the postulates, but other properties like the single model property that you have in the rational closure case, or
right.
this kind of a more meta level properties, not just the postulates, but also the postulates. But I mean, maybe you definitely get some more postulates as well because you have a more expressive language. But in terms of, I don't know, computation and this kind of meta level properties, if you want.
Right. I think so. The two things that I'm willing to say is that I think adding disjunction to your typical or your defeasible inferences would probably could possibly do something very bad to the computation, because disjunction is kind of the enemy of efficiency in some sense. Um, I would say that the extension that I would find most interesting to see how it affects these kinds of properties would be the negative the negative twiddle, saying that a alpha does not typically imply beta, because I think that can lead to some interesting ideas in the semantics, because there are many. So is that saying essentially that it is not the case? Is it simply saying that it is not the case that all of the minimal models of the left are models of the right? Or is it maybe saying something more than that? So depending, I need to look at the paper properly to see how that would be defined. I don't know if Tommy could say something about that, but that would be that. I think the negative twiddle would be a very interesting it'd be very interesting to see how that affects these kinds of properties, like the minimal model property of rational closure, and that's off the top of my head.
Okay, thank you. We have a
Uh,
question by Joel Hamilton.
Hi, Adam. Thanks for the talk. This may not have a quick answer, so if it doesn't, like, you can just tell me that you'll chat to me afterwards or something. But I just want to ask if you could just like quickly summarize, like algorithmically, how do prototypical and presumptive reasoning go about reasoning like conservatively and adventurously, respectively? Like, how do their algorithms actually differ? But if it's too long of an answer, we can chat separately.
So I can try to make it quick. We can also chat separately if you have more questions. But if you think back to the rank model, so if you, visually speaking, if you have a conservative pattern of reasoning, your rank model will have as few levels, as few ranks as possible. You squash the model down as much as possible. And that is what is meant by rational closure having the minimal model property. It is the number of ranks are as minimal as possible. And in that sense, you get that has an influence on the kind of reasoning or the kind of conservative pattern of reasoning that you get. Whereas a more presumptive entailment, like say lexicographic closure, has many, many ranks. And this allows for many levels of typicality and a more adventurous nature. And the way that translates algorithmically is that the algorithms for these entailment relations are done via ranks on the actual statements in your knowledge base. And these ranks on the statements in knowledge base are informed by those minimal models. And so the algorithm for a rational closure would have, maybe a few ranks that it assigns to those statements, and then it takes them away one by one and sees until it finds a level that satisfies your query. Whereas for a presumptive relation like lexicographic closure, you have many more ranks. And so you throw away fewer statements at a time until you find a subset that is consistent with your query, or that entails your query.
That makes perfect sense, because less ranks kind of means lower ranks, and it means that everything is just basically seen as more typical. Yeah, so thanks.
Yeah.
Okay, any other questions? So I may have one more question, if you don't mind. So
Okay.
the way things are usually done, at least in the KLM tradition, you start with some classical semantics, some classical language. Can be propositional logic, modal logic, description logics, and then you build up the whole thing. Now, what if we just start with some non-classical semantics? For example, you can have a propositional language with a non-classical semantics, for example, some fuzzy or even some form of paraconsistent logic. And then you build the whole defeasible reasoning thing. So my question is, does that make sense? Has it been done before? Or so what is your view?
So I won't say that something hasn't been done before, because it's obviously entirely possible that I have missed it. What I will say is that something that I don't think, that I think has not been done before, that I have some kind of knowledge that it hasn't, is enriching something like a probabilistic logic with typicality or defeasibility. So that's something that I think would be very interesting if you start with a probabilistic logic, where you can also consider a fuzzy logic, where you have a degree, you give it some real number, and then you enrich that with some kind of typicality connective, like a twiddle, and you construct some kind of ranked. I mean, I'm spitballing, but I think that would be I think that is a very interesting approach that I would be interested in looking at. If you start with some kind of, take a non-classical or probabilistic formalism or logic or starting point, and then try to enrich it with some kind of defeasibility, I think would be a very interesting avenue of research. But I can't say that it hasn't been done before, but I don't know of any approaches. Yeah.
Okay, thank you very much. So I think that time is up. Thank you.